Okay, so here's a bottle of gas, basically molecules bouncing around. And if we focus on the bottom of the bottle, and specifically two areas, a 1 centimeter squared area and a 2 centimeter squared area, the bouncing of the gas molecules causes an average force over time on each surface. So is the force bigger on the smaller surface or the bigger surface? The average force is twice as big on the big surface because twice as many particles are bouncing off of it. Now let's think about the pressure that the gas molecules are putting on both of these surfaces. Is the pressure bigger on the small surface or the big surface? The pressure on the smaller square and the bigger square are exactly the same. Actually, the pressure around the entire bottle is exactly the same, but it's easy to see for these two, because we can write P1, which is the pressure on the smaller square, is equal to F1, which is the average force from all the particles bouncing off the smaller square, divided by A1, the area of the smaller square, which we know is just 1 centimeter squared. Now we can write the pressure on the bigger square is equal to, well, let's write this in terms of the force and area from the smaller square. So we know the force on the bigger square is going to be just twice the force on the smaller square because twice as many particles are bouncing off of it. So we have 2F1. And the area is also twice as big, so this is 2A1. Cancel out the 2's, this is just F1 over A1, which is the same as the pressure on the smaller square. The molecules are moving at a particular speed. That means the gas is at a certain temperature. But what would happen to the temperature if we increase the speed of the particles so the typical speed is twice as big? So when we say typical velocity, we mean v RMS, which is just equal to the square root of the average v squareds of the particles. And we can relate this to the temperature by 1/2 mass of the particles, v RMS squared, is equal to 3/2 Boltzmann's constant times temperature. And we can rewrite this to get just temperature by itself on the left. It's temperature equals mass over 3 times Boltzmann's constant times VRMS squared. And we can use this to figure out what happens when you increase the velocity by a factor of 2. So to do this, just write your initial temperature is equal to, we have our constants here, just using this equation, and then call the initial velocity VI, and it's squared. Now write our final temperature, TF. Now again, we have the same constants, but the velocity here is going to be 2 times the original velocity. So we have 2 VI is our velocity, and that's squared. Now the squared goes on the 2, and the squared goes on the VI, and so I'll bring the 2 squared, which is 4, out front, and that'll be 4, and then again we have our constants here, and then the squared on the VI squared, and then notice that this here is exactly the same as the initial temperature, but then we have a factor of 4, so this is equal to 4 times Ti. So the final temperature is equal, this is Tf, the final temperature is equal to 4 times the initial temperature. Now again, if we increase the velocity of the particles, so the typical speed is twice as big, what happens to the pressure? Here we just use pressure times volume equals number of particles, Boltzmann's constant times temperature. That good equation. We know that the volume is constant, the bottle doesn't change size, the number of particles is the same, none leave or come in, and Boltzmann's constant doesn't change. So if on the right-hand side we know that temperature goes up by a factor of 4, the only way the left-hand side can go up by a factor of 4 is if pressure also goes up by a factor of 4. So instead of changing the speed of the particles, what if we take each particle and change the mass so that it's twice as massive? What happens to the pressure and what happens to the temperature? So for this one, you might just be able to see straight from this equation that we used before that if you increase the mass by a factor of 2, then you have to increase the temperature by a factor of 2 also. Or another way to see it is similar to what we did before when we found the increase in temperature from the increase in velocity, is we write Ti is equal to, so just rearrange this as V RMS squared over 3 kb times some initial mass, and then we can write the final temperature is equal to this same thing in parentheses times, now the mass is twice as big, so it's 2 mi. And it's easy to see here that this and this are the same as what we have up here, and now we just have an extra factor of 2. So what that means is that we can write this as 2 times the initial temperature. So the final temperature is 2 times as big as the initial temperature. Here we can just use PV equals NkBT. The volume's a constant, doesn't change. Number of particles in Kb also constant. So if temperature on the right goes up by a factor of 2, and we want the left-hand side to also equal that, so it goes up by a factor of 2, the only way to do that is if pressure also goes up by a factor of 2.